Have you ever just stopped and looked around at a massive skyscraper or a huge highway and wondered, what's literally holding all of this together? What unseen gray powder acts as the literal glue for our modern world? Okay, let's dive into this. Welcome to today's Explainer. We're going to be looking at cement, but we're going to treat the production of cement exactly like what it actually is, a high-stakes, extremely precise baking recipe that quite literally builds human civilization. Here's how we're breaking it down today. First, the ultimate binding material. Then, the magic cement recipe. After that, we'll get into chemical superpowers and clinkers, forging in the kiln, and finally, testing the limits. All right, let's kick things off with Section 1, the ultimate binding material. Think of cement as the industrial superglue. It's the ultimate binder that locks coarse aggregates, sand, and water together to make concrete. Without it, our entire world would literally crumble into dust under its own weight. And the crazy thing is, it all started way back in 1824. An innovator named Joseph Aspdin invented Portland cement over in the UK. He actually named it after the local Portland stone just because the colors matched. Fast forward to today, and it is still the absolute irreplaceable foundation of global infrastructure. Seriously, with all our modern tech, we really haven't found a better alternative. Moving right along to Section 2, the magic cement recipe. Now, remember how I said it's like baking a cake? Well, getting the exact percentages of your raw materials is make or break. If you mess up this recipe, the final strength of the cement completely fails. Lime is the absolute heavy hitter here, making up about 62 to 65%. Then you've got silica at 17 to 25% and alumina at 3 to 8%. Gypsum and iron oxide hover around 3 to 4% each. And finally, you throw in some trace elements like magnesia, sulfur, and alkalis for that last tiny sliver. Nailing these ratios is just this brilliant, delicate balancing act. So what do all these ingredients actually do? Well, lime and silica are bringing the bulk and the core structural strength. Alumina, that acts almost like a quick-setting yeast. Then there's gypsum. Gypsum is an incredibly crucial retarder. It intentionally delays the setting time so construction workers actually have time to work with the wet cement. Iron oxide fuses everything together when it gets heated up, and it's also what gives cement that iconic reddish-brown tint. But you really gotta watch out for the trace risks. Too much lime, magnesia, or sulfur causes what engineers call unsoundness, which is a ruinous volume expansion that literally cracks the concrete from the inside out. No way do you want that. And excess alkalis, they cause those ugly white spots called efflorescence that you sometimes see on brickwork. All right, into Section 3, chemical superpowers and clinkers. When our raw ingredients finally bake together under the heat, they form these things called Bogues compounds. You can think of these as the microscopic chemical superpowers of our recipe. Now, what's really interesting here is the contrast between our two main silicates. Tricalcium silicate, or alite, is totally your sprinter. It gives the cement its initial strength within the first 7 days, boasts the best overall cementing property, and makes up 45 to 85% of well-burnt clinkers. Dicalcium silicate, or bolite, on the other hand, plays the long game. It provides progressive, final strength and can take up to an entire year to fully contribute. It is absolutely perfect for later-stage structural integrity. Then we get to the aluminates. Tricalcium aluminate, also known as selite, causes the immediate flash set and releases the absolute maximum total heat of hydration. Meanwhile, tetracalcium aluminoferrate, or phyllite, also triggers a flash set, but its superpower is having the highest rate of heat release. So even if its total overall heat isn't the highest, it releases it insanely fast. They act fast and they run super hot. To activate all of these chemical superpowers, you need exactly 38% water by weight. That breaks down to 23% for the actual chemical hydration process, and 15% just to fill the microscopic voids in the mixture. But be incredibly careful here. If you add too much water, you will severely ruin the overall strength of the cement by completely diluting the chemistry, so precision is key. Let's move to Section 4, forging in the kiln. Now we are entering the massive manufacturing kilns, and honestly, it's a pretty dramatic process. First up, we mix the ingredients, either by dry blending them or creating a wet slurry. Next, we preheat that mix up to 800 degrees Celsius. But step 3 is the real forge. We burn it in a massive rotary kiln at absolutely extreme temperatures. We're talking between 1400 and 1500 degrees Celsius. This intense heat physically fuses the ingredients into these tiny, hard nodules called clinkers. Finally, we grind those clinkers down into the superfine gray powder that we're all familiar with. And finally, Section 5, testing the limits. Look, we can't just ship this powder off to build a skyscraper without some rigorous quality control. There are two main testing arenas. First, you have the quick on-site field tests. A worker is basically just checking if the color is a uniform gray, if it feels nice and smooth between the fingers, and if a handful initially sinks in water rather than instantly clumping up into big lumps. But then we get to the highly controlled laboratory tests, and these dive super deep into fineness, consistency, soundness, and highly precise setting times. In the lab, fineness is absolutely critical. To give you an idea of just how fine we're talking, they use an IS sieve number 9, which is a mere 90 microns wide, to ensure over 90% of the cement easily passes right through. They also use Blaine's air permeability test to make sure the specific surface area is greater than 2250 square centimeters per gram for ordinary Portland cement. But before we can even test setting times, we absolutely have to find the standard consistency, which is denoted as P, using a very specialized device called the Vicat apparatus. So the crucial point here is just how insanely exact this consistency test really is. The Vicat apparatus uses a 50mm high, 10mm diameter plunger. They carefully add water to the cement until this plunger penetrates exactly 33 to 35 millimeters from the top of a 40mm mold. Once we hit that exact microscopic dimension, boom, we've found our standard consistency, P. And this single value completely dictates the exact water ratio used for all our subsequent lab tests. Now, using 85% of that P water value, we test the setting times. For ordinary Portland cement, it loses its plasticity, which is known as its initial setting time, in just 30 minutes. And then it completely hardens, reaching its final setting time in about 10 hours. But wait a second. If it starts setting in just 30 minutes, how in the world do construction workers manage on site without it drying up? Well, masonry cement actually has a 90-minute initial setting time and a 24-hour final setting time. As our source amusingly points out, this extended window is exactly why masons can take their much-needed tea breaks without the mortar turning into a solid rock right there in the bucket. Next up, we've got a test for soundness to guarantee the cement won't dangerously expand and crack once it finally sets. We use two methods for this. The Le Chatelet apparatus tests for excess lime. It uses a small 30mm mold where the indicator arms must not expand more than 10mm after boiling, all while using 78% of that P water value. The autoclave test, however, steps it up and tests for both lime and magnesia. And guys, we're talking about subjecting the cement to a violent 21 kilograms per square centimeter of steam pressure for 3 straight hours. Even under those brutal conditions, the expansion must remain strictly under 0.8%. Finally, we wrap up the lab tests by measuring raw physical strength. For the compressive test, we literally crush 70.5mm cubes made of a 1:3 cement to sand ratio. We use incredibly specific math for the water here, and we expect them to reach a massive 33 newtons per square millimeter in 28 days. The tensile test literally snaps briquette molds to quickly ID any quality defects. And we even test specific gravity using a Leach Tilia flask filled with kerosene, because obviously using water would instantly cause a chemical reaction. This helps us find a precise value of around 3.15. Honestly, it's just an intense physical gauntlet. And this brilliantly illustrates just how incredibly complex and fine-tuned this everyday material actually is. From a simple 1824 invention to the highly tested, chemically balanced recipe we rely on right now, cement is the literal foundation of modern human existence. It's an absolute engineering marvel, just masquerading as gray dust. So will human innovation ever find an alternative to Joseph Aspidin's invention, or are we forever bound by the magic of clinkers and hydration? Think about that the next time you walk on a sidewalk or cross a bridge. Thanks for joining me on this explainer, and keep questioning the world around you.